Okay, so let's look at this question which came in CAT 24. It is talking about two sets. So you have sets A with 6 elements and sets B with 3 elements, and it wants us to map these elements from A to B so that there is one mapping for each element here in A, but every element, the requirement is that every element should be definitely mapped. So all the elements of A should be mapped to exactly one element in B, and element in B should definitely be mapped. So there should be not a there should not be a scenario, for example, just like this, in which you could say that this element is not there, is not mapped. Okay, and in that scenario, that need not be counted. So if it was like this, then this is not a desirable situation. Now I will solve this question in two different ways. One is a standard way, which I would believe that every CAT aspirant should be able to solve. And the other would be a slightly advanced way in which I would tell you how you could do it, and maybe you will get to learn something new. Okay, so the standard way is, so if you look at this question primarily, I see that this question is basically something like putting uh, uh, 6 different balls in 3 different boxes such that no box is empty. So it's very similar to that. Yeah. Or yeah. So this is one of the analogies that you can get from this question. Now to do this question, one way, the standard way would be that let us make cases so that no box is left out, and let's split those balls or these numbers in A to numbers in B so that no number in B is left out. Okay. Now the standard that I follow, I normally follow a structure in which so that I don't miss out on anything, is this, that since there are 3 elements, I will split these 6 elements, three elements that I need to map into it. So from A, I will take those 6 elements and I will break them into 3 groups such that every group has at least one element in it. So I follow a structure of a non-decreasing breaking up, which means if I have 3 groups, let me say that, okay, so 1 as a digit needs to be mapped, 8 as a digit needs to be mapped, and 27 as a digit needs to be mapped. How many mappings will go to 1? So I'll start in a non-decreasing way. It has to be at least 1. Then I'll make this as 1, and then all the remaining will go here. So this is one case. The other case would be, since this is 1 again, so this, now I'll change this 1 to 2, and obviously I'm left with 3. So if you realize, the reason I'm doing it like this is because I want to make sure that my subsequent digit is never smaller than my previous digit. Now, if I were to continue with 1 here, I would end up getting, next step would be getting 1 and a 3, which would make the digit under 27 to be 2. So that will not work. So this is the case that will happen. So I have taken care of all the one situations when 1 will get exactly 1. The next will be 2. And once it's 2, then obviously this cannot be less than 2. This will be 2 and 2. So these are 3 cases that you will get. If these are 3 cases that you get, now we need to figure out how many answers are possible. So what I will do is, now the standard way of doing this is, I will take 6, I'll do 6C1, then I'll be left with 5, I'll do 5C1, and then I'll have 4C4. Right? Now this can be arranged in how many ways? Obviously this 4 can be here, or here, or here. So there are 3 ways, or 3 factorial by 2 factorial ways. So I will just do this 3 factorial by 2 factorial. This is the case I have solved for this case. Similarly, I will solve this question with the next situation. Now all 3 are different, so obviously it will be 3 factorial in that case. So I will do a 6C1, and then I'll do a 5C2. I'm left with 3 elements, which is 3C3. Good idea to write the last one also, because you know what you're doing. And then all 3 are different. This will be 3 factorial times. So these would get added. Then the third case would get added to this. And the third case in this scenario would be all of them are same. So this is very simple. This will be 6C2, 4C2, and 2C2. And obviously this is cannot be permuted anymore because all the 2's are same. So it's 3 factorial by 3 factorial. So you want to do this 3 factorial by 3 factorial, you will get 1. So you need not worry about this. Right? So let's just solve this and find the answer. So 6C1 is 6 into 5. Last one is always 1. So I need not worry. Into 3 plus 6 into 5C2 is 10. Again 1 into 6 plus I get 62. 62 is 15. Yeah, and 4C2 is 6. Again into 1 and into 1. I just need to add them up. So let's just do this. So I get what? I get 90 plus this 36 is 60. And I get a plus of 90 again. I add them up. So I get 450 plus 90 is 540. So that is our answer. So you could have done it this way and we would have been able to solve it like this. There is another way to solve this question. For those students who are slightly advanced, right, or who have studied something called principle of inclusion and exclusion, they could have done this in another way. Now, in that case, I will just show you how you could have done it. It would have been the total number of ways would have been 3 to power 6, putting all the boxes, so every ball could go into any of the three boxes. So all the mappings that were happening would happen in any of the three ways. Every element in A could have gone to any one of the elements there. So you had 6 elements here, right? And then you had some elements here. So you had A and B. So every element could go into 3 ways. Yeah. Similarly for this. So you have 3 to the power 6 ways. Now we want to exclude those ways in which something is not happening. Some of the elements are not mapped. So directly I would have done 3 to the power 6 minus 3C2, 2 to the power 6 plus 3C1, 1 to the power 6. And obviously the next case will not exist. So this could have been done in one line like this. Now I will tell you how we have arrived at this figure, but just let's calculate the answer for the time being. So 3 to the power 6 is 9 cube, which is 729. This is minus 3C2 is 3, 2 to the power 6 is 64, and this would have been just 3. So let's just do this math a little bit. So the 3 gets added to it, this becomes 732. And from 732, we subtract 180 plus 12 is 192. When you subtract this, you get 540. Yes, we get the same answer. Obviously, this would have been faster. You could have done in one step, but it would require some knowledge about certain principles. So what we have done out here is, let me just explain it to you. What we have done is, I have used something called principle of inclusion and exclusion, which is nothing but a simple scenario, a simplified, a generalized way to look at union values in sets. So I will now, what I'll do is I'll tell you, so let's define 3 sets. One set I will define is would be one's complement. Let's say, what is this set? This is a set of all mappings in which one is missing. So let's call this set X. Okay. So similarly, I can define another set of 8 complements, which I'll call Y, right? And then I will do a 27 complement set, which I'll call Z. So what I'm basically looking at is that I'm finding the total number of solutions, which are 3 to the power 6. From that, I will subtract what? The number of elements in X union Y union Z. So what does this mean? It means one is definitely, X is a set in which one is definitely missing. 8 is a set, 8 complement Y is a set in which 8 is definitely missing, Z is a set in which 27 is definitely missing. So that means all the elements in X are being mapped to two possible out elements in B, which are 8 and 27. So for that, what we'll do is we will take which element is missing or which 2 elements to choose, and all the 6 elements will be mapped to that 2 to the power 6. So this thing actually is nothing but nx plus ny plus nz, right? From this, I will now, so I've got this value. Obviously, now I need to subtract minus nx intersection y. And nx intersection z. And ny intersection z. The third element, which would have been in this case, That all three are missing would not be possible. Why? Because they all the digits have been mapped to at least one of them. So that third part was zero. So you need not worry about it. Now let's look at what is nx. Nx is when one is missing. That means you could one is definitely missing. So you could have two missing or eight missing, but one is definitely missing. So nx is what? All the six elements getting mapped to 8 and 27 is 2 to power 6, right? And this is also 2 to power 6, and this is also 2 to power 6. So they get mapped here, and this is what you get. Similarly, this is a set in which both 1 and 8 are missing. That means everything is getting mapped to 27 only. That means this is 1, this is 1, and this is 1. And this is exactly what we have done. So this is nothing but 1 to power 6, 1 to power 6, 1 to power 6. If you look at it, this is what this term is. Yeah, this is what this term is. And this is the total number of ways, and you still get the same answer. Now you could generalize this principle. If you want to know more about it, you could actually go about, figure this out, search on Google. You will find a lot of links explaining this principle. So you could have gone, and the general formula for this would have then become something like this. Let's say we had, instead of this, we had 4 elements. Okay, then in that case, you could have directly done this like this. 4 to power 6 minus, now we start doing our inclusion principle. We'll have 4 sets, 3 are used, 1 is not used, so you'll get 3 to power 6. Yeah, then we do a minus, only 2 being used, it's 2 to power 6. Then exactly 1 being used, then we'll do a plus here, we'll do 4c3, 1 to power 6. And this would have also given us an answer had there been a 4th element here. So I just wanted to, if you know this, it can help you solve. Otherwise, our initial solution was good enough, which should be sufficient for us to manage in CAT. Thank you very much.